It is a perfect afternoon on the water. We are looking at a massive luxury timber deck sitting right on the edge of the surf. This pavilion was engineered to withstand hurricane-force winds. Yet right now, under clear skies and a light breeze, structural failure is imminent. With zero warning, a major section of the deck gives way, crashing into the sand under nothing more than its own weight. Inspect the wreckage. The heavy wooden beams are intact. The concrete pilings haven't even cracked. This collapse was caused entirely by the silent failure of the structure's most neglected components, the fasteners. This map highlights the high-risk perimeter. The coastal zone is a specific environment that extends up to 2 miles inland from the surf. The air inside this zone is continuously loaded with moisture, salt spray, and highly reactive chlorides. Fasteners endure the highest persistent physical forces in any building. When you expose those tiny load-bearing elements to a constant chemical bath, microscopic rot quickly scales up to a structural threat. To see how these connections fail, we must look at the microscopic level of a standard steel bolt inside a timber joint. This cross-section illustrates chloride attack. Airborne salt chemically bombards the metal, eating away its thin protective boundary layer. Once stripped, the exposed metal oxidizes. This creates a brownish discoloration known as tea-staining. The damage rarely stops at the surface. It accelerates into deep, jagged craters, a process called pitting that physically hollows out the metal's core thickness. There is a second threat that plagues coastal construction: galvanic corrosion. This is triggered when builders mix two dissimilar metals. We have a standard steel bolt tightened against an aluminum hinge. Salt water seeping into the microscopic gap acts as an electrolyte, turning the mismatched metals into an active battery. Current flows through the joint, dissolving the weaker steel bolt while leaving the aluminum untouched. Without specific chemical defenses, this reaction will silently sever the load paths of a building from the inside out. Defeating this environment requires abandoning standard hardware for a specific metallurgical antidote: marine-grade alloys. For direct saltwater exposure, the gold standard is 316 stainless steel. What separates the 316 grade from weaker alloys is the addition of an element called molybdenum. Notice how the molybdenum atoms form a rebounding shield. When chloride ions strike the surface, this barrier neutralizes the stress and repels the salt, stopping pitting on contact. Extreme environments require heavier defenses, like duplex 2205 stainless steel, solid titanium, or heavy polymer coatings. Selecting a marine-grade alloy serves a distinct structural purpose. It is a chemical requirement for a building's survival on the coast. Upgrading a single bolt is only the first step. A coastal structure relies on a vast array of interconnected hardware, from brackets and tension rods to heavy track systems and wire rope. To prevent the battery effect of galvanic corrosion, all hardware in a structural joint must be strictly metallurgically matched. The design of those joints is equally important. Builders must use sealed bearings and engineer proper drainage so moisture is never allowed to sit in the crevices. The final irony of this advanced metallurgy is how you protect it, by simply flushing it with fresh water and applying marine-grade lithium grease. Even the most advanced alloys will eventually fail if the system design allows salt crystals to sit and concentrate. When properly engineered from the inside out, a coastal structure can easily absorb a massive, high-energy storm. We cannot stop the physical forces of the ocean or the aggressive chemistry of the coast. True structural resilience is only achieved by out-engineering nature at the microscopic level. The structures that survive for decades are built on a specific engineering reality. The endurance of the entire frame is only